Hi, my name is Lauritz van Luijk. I will talk about pure state entanglement and von Neumann algebras. This talk is based on joint work with Alex Stadtmeister, Reinhard Werner, and Henrik Wilming. We sadly could not be there for this QIP, as you notice, but we're very happy that we can give this talk as an online recorded presentation. If you have any questions, please reach out to us, and I'm sure that you all had a wonderful time there. We thank the organizers very much. Okay, let's get into it. Entanglement, what is that? Entanglement is, by definition, the resource that cannot be created by local operations and classical communication. We can take this very definition to broader settings than the usual one in finite dimensional quantum info, once we know what local operations are. But before we get into that, let's look at a typical example of an LOCC protocol. We would have a bipartite system, and Alice maybe performs a local measurement. Then she gets an outcome. She communicates that outcome to Bob. Bob receives it and does a conditional operation, conditioned on what he received. And then he will perform a local measurement, send the outcome to Alice back. She does something, and so on. One particular use case of this is the teleportation protocol. So here Alice has a state psi A, which she wishes to teleport to Bob, and they also share an entangled Bell state. And then she would do a measurement in a Bell basis, communicate the outcome. Bob would do the conditional XZ unitary and get this very state psi. So yeah, teleportation works. You all know that, I guess. And we can now look at LOCC in a much more broader setting. With LOCC defined, we have a comparative theory of entanglement. So we can say that one pure state psi is more entangled than another pure state phi, once we can find an LOCC protocol that takes us from psi to phi. And for this entanglement ordering, we can allow for arbitrarily small errors. So we say psi is more entangled than phi if, for an arbitrarily small error, epsilon, I can go in norm epsilon close from psi to phi with LOCC. And the possible entanglement transitions, transitions with LOCC are characterized precisely by Nielsen's theorem in finite dimensional systems. And, systems with finitely many degrees of freedom, those can of course have infinite dimensional Hilbert spaces, like a harmonic oscillator maybe. But that's not a system with true physical, infinitely many physical degrees of freedom. Those are systems, for example, in many-body physics, where I have a quantum gas in the thermodynamic limit, or where I may be already in a quantum field theory, or setups in quantum information theory, where, let's say, Alice and Bob share an unlimited amount of entangled Bell pairs. Then I can model that by saying they share infinitely many, and then we have infinitely many degrees of freedom. So to describe systems like that, we need another language. This language requires that we move from the usual tensor product framework to the commuting operator framework. The commuting operator framework is formulated in von Neumann algebras. So what is a von Neumann algebra? It is the observable algebra of the quantum system that we're interested in. It acts on a Hilbert space H, and it is an algebra of bounded operators on that Hilbert space, which is closed under the adjoint, it's closed under products, but it's also closed in the strong operator topology. And the observables of this very quantum system that we're modeling are then described by self-adjoint operators in this algebra, or actually POVMs with values in the observable algebra. The states are just density operators on the Hilbert space because, well, that's somehow the ambient standard quantum system. But what's relevant for the quantum system described by the von Neumann algebra is the reduced state, the reduction of this density operator to the algebra. And that is then a positive linear functional from the algebra into the complex numbers, which is continuous in some appropriate sense. So we have now definitions for observables and states, but of course we want to talk about LOCC, so we also need to talk about channels. Well, first of all, a quantum channel on the system that is described by this ambient Hilbert space, that's just a CPTP map on the trace class. We call that a global channel. So a global channel is a CPTP map on the trace class of the Hilbert space, with the additional assumption that T star, the adjoint, the Heisenberg picture channel, takes the von Neumann algebra, the observable algebra, into itself. And we distinguish this from what we call an inner channel. An inner channel is one that has a Krauss decomposition with Krauss operators in the von Neumann algebra. We'll see shortly that those two notions are not the same, and that's very much connected to bipartite systems. What is a bipartite system? A bipartite system in this language is, well, still one Hilbert space, but I don't have one von Neumann algebra, I have two. And in the following, these will be commuting factors. I'll say what a factor is shortly. Commuting just means that all observables of Alice, so all observables in MA, commute with those of Bob. The observables, the operators in MB. Now, what is a factor? A factor is a von Neumann algebra that has no classical degrees of freedom, so it has no center, or the center is trivial. The center is the intersection of M and its commutant. The commutant is the observable algebra, the von Neumann algebra, containing all operators that commute with a given von Neumann algebra. So again, bipartite system, two factors, and they commute. We will make an additional assumption in this talk, which is called Haack duality. Haack duality states that these two factors are commutants of each other. So any unitary that commutes with all observables of Alice will be a unitary of Bob. Any symmetry of Alice is an element of Bob. Okay, so with this notion of bipartite systems, we'll do the following. We'll talk about local operations. Locality preserving operation is now a CP-TP map on the Hilbert space with the property that it takes Alice's observable algebras to Alice's observable algebra, and likewise for Bob. And it has the additional property that it factorizes over A and B observables. So it satisfies this algebraic identity there. And you might think this is all that we need to ask for. But we haven't, in the tensor product framework, that is true. In the tensor product, this is all that we have to ask for. The locality preserving channel is a product channel. But we'll see that this is not the same in our setting. So we say that a quantum channel, the CP-TP map on T of H, is local to Alice if, well, it takes Alice's observables to Alice's observables, but it also leaves invariant Bob's observables. So it acts as the identity there. And now we have the following lemma. A channel is local to Alice if and only if it's inner for Alice's von Neumann algebra. So if and only if it admits a Krauss decomposition with Krauss operators from Alice's observable algebra. And we say that something is a product channel if it is a product of a channel that is local to Alice and a channel that is local to Bob. And these two kinds of channels, they commute, so the order doesn't matter. And yeah, I said it already, locality preserving does not imply being a product channel. And here is a very nice example of that. We consider a quantum field theory on Minkowski space, and Alice has the left wedge and Bob has the right wedge, Rindler wedge. And it's depicted here with a Penrose diagram on the slide. And the channel that we'll look at is the boost. The boost in direction of these wedges. The boost leaves invariant these wedges, like geometrically, but it's not a product channel. It's not the case that the left side of Minkowski space can somehow do a boost while the right-hand side does not boost. So this property that the boost can be implemented locally by Alice and in such a way that it leaves invariant Bob's observables, that is not true. It's not satisfied here. So we see locality preserving and being product channel is not the same. So the correct notion of local operations is that of product channels with inner channels. And with that, we can now define LOCC, and we just define it in the same way as always with Krauss operators. So we have now our definition for two vectors in our Hilbert space. When is one LOCC with LOCC mappable to the other one? Good. So now, what about Nielsen's theorem? Nielsen's theorem actually does carry over perfectly. So we fix our bipartite system, we fix two bipartite pure states, psi and phi, and we consider the marginal states, psi a and phi a. These are the functionals that these states induce on Alice's von Neumann algebra. And then Nielsen's theorem states the following. Psi, we can go from psi to phi with LOCC if and only if we have majorization between psi a and phi a. So if and only if there exist unitaries, well, actually it's partial isometries here, and convex combination coefficients such that we can write psi a as the mixture of these unitary rotations of phi a. And the proof sketch is, well, easy. What you do is you learn a bit about von Neumann algebras, and you learn something called Tomita-Takasaki modular theory. And equipped with that tool, you then go back to Nielsen and Chuang and you read up on how this is proved in the normal setting. And then you take the objects like rho to the 1/2 times sigma to the -1/2 and replace them by the corresponding objects in Tomita-Takasaki theory. And then you can use some of the same proof, essentially, and it will go through with some technicalities. But yeah, the broad idea is just basically do the same as in the finite dimensional settings, but use Tomita-Takasaki theory to well, make it mathematically correct. Okay. Yeah, this was proved by Jason Crenn and others in a slightly more constrained setting, and then we did it for general von Neumann algebras. I'll very briefly tell you about the classification of factors. Factors are classified into 3 types, 1, 2, and 3. And type 1 comes in subtypes 1n. These are matrix algebras, B of H, and n is the dimension of the Hilbert space. Type 2 comes with 2 subcases, type 2, 1 and type 2 infinity, and type 3 has a continuum, type 3 lambda, the lambda from 0 to 1. You don't need to know anything about these except for, well, type 1 is the usual quantum mechanics stuff, and the others one are somehow mathematically classified and whatever. What we'll show in the following is, or I'll tell you, is that the type and subtype are in one-to-one correspondence with operational entanglement properties. And to do that, we start off with a very easy entanglement property, which is one-shot entanglement. How much is there? We say that a state has an infinity of one-shot entanglement if for every finite dimensional bipartite state psi, we can distill it. So there is an LOCC protocol that takes us from omega to omega prime tensor psi for some state omega prime. And if this should be possible for all psi. And then the following are equivalent. The algebras are of type 2 or 3 if and only if some or all pure states have infinite one-shot entanglement. But now we want to distinguish types 2 and 3, and this is done by the following. Type 3 is corresponds precisely to the case where LOCC trivializes. So where all pure states psi and phi are equally entangled in the sense that I can, for an arbitrarily small error epsilon, go from psi to phi with LOCC and vice versa. Now we had these subtypes, right? We had type 2, 1 and type 3 lambda. And we'd also like to distinguish those. This table summarizes what we have done so far, but yeah, subtypes. First, we start off with maximally entangled states. A state is maximally entangled if and only if it's more entangled than every other state. So for every other state psi, we can go from omega to that state psi with an arbitrarily small error. And then such states, maximally entangled ones, they exist precisely in types 1n, 2, 1, and 3 lambda. But they do not exist in 1 infinity and 2 infinity. Now we have that, and we would like to understand the type 3 subtypes, because what we have done so far distinguishes all of these types from each other except for the type 3 subtypes. For that, we need something that we presented at the last QIP as a plenary talk. We need the concept of embezzlement of entanglement. And I'll not explain what it is precisely, but there's this quantifier called kappa max that quantifies operationally how good a system is at being a resource for the task of embezzlement of entanglement. And 2 is the worst case. So if kappa max equals 2, then the system is no good at all. But if kappa max is smaller, then the system can do embezzlement of entanglement. We see that in the type 3 lambda case, we have an interesting function that depends on lambda. And actually, this function is invertible. And we can invert it. And we have a formula that computes lambda from kappa max. So with this, we can deduce from operational entanglement properties which type 3 subtype we have. So to summarize that, we have a one-to-one correspondence between the type classification of von Neumann algebras and operational entanglement properties. And now I will give a very short outlook on what we do with that. So first, in the type 2 case, where LOCC does not trivialize, we can have interesting entanglement monotones. We can define a Schmidt spectrum and we can define a Schmidt rank. The Schmidt rank, like in the finite dimensional case, precisely characterizes which stochastic LOCC transitions are possible. And we can also define majorization based on the spectrum for the reduced states and do some nice majorization theory. And from that, we can define entanglement monotones. And then we have like Renyi alpha entanglement entropies and all that. And they work, they're entanglement monotones. And all that is discussed in our paper. Another outlook is an application to many-body systems. So now we look at quantum many-body systems in the thermodynamic limit. And here, if I do a bipartition into infinite chunks of the system, then I get to von Neumann algebras describing these two chunks in the ground state sector, and they will commute. And if we assume Haack duality, then we can now link the classification of these von Neumann algebras to the entanglement properties that are present in the ground state sector. And yeah, so we can compute the ground state sector's von Neumann algebraic type, say it's type 3, and then we can deduce, well, the LOCC theory in the ground state sector trivializes. We know that in two-dimensional gapped ground states, all types can appear. We have a construction that shows that, even for translation invariant gapped ground states, in the trivial topological phase, this can happen. This will be discussed in a forthcoming paper that should appear in the next weeks. Good. So here's a short slide with a summary of all that we discussed. Bipartite quantum systems in the von Neumann algebraic quantum information theory are described by commuting factors on Hilbert space. The single-shot entanglement properties of all pure states on this Hilbert space are in one-to-one correspondence with the algebraic type of these factors that describe Alice and Bob's algebra. And the LOCC transitions between individual pure states, whether they're possible or not, is precisely characterized by Nielsen's theorem by majorization theory. And in type 3, well, it's always possible because LOCC trivializes. And with that, I'd like to thank you for your attention and hope you have a good conference.